Good afternoon, everyone. I'm Wei Shen, a second-year PhD student at the ANU. And today I'll be talking about the survey of extremely metal-poor stars in the Magellanic Clouds. And my supervisors are Ken, Dougal, Gary, and Thomas. So here's my talk outline. I'll first introduce what EMP stars are all about, followed by talking about the survey of these stars in the Magellanic Clouds. And I'll end off by touching on follow-up plans using high-resolution spectroscopy. So what are extremely metal-poor stars? Also known as EMP stars, these stars have an Fe/H ratio of less than -3. And despite not being the metal-free first-generation stars, they are the oldest stars that we can observe directly in the universe, as far as we know. These stars can shed light on the properties of the first stars as they are formed from the material from the first supernovae, and they can tell us how they may have entered the galactic halo through their whole system's accretion. So some background on EMP stars in dwarf galaxies. They are much less well studied than EMP stars in the galactic halo, simply because of their large distances. And EMP stars seem to be more common in the ultra-faint dwarf galaxies, such as Reticulum 2, as compared to classical dwarfs such as the LMC, Fornax, and Sculptor. And compared to EMP stars in the Milky Way halo, there seems to be some important differences in key elements such as carbon, alpha, and neutron capture elements that appear to correlate with the mass of the galaxy. So despite all that we know about EMP stars, it is not clear whether they exist in galaxies intermediate between the faintest dwarfs and the giant Milky Way, such as the Magellanic Clouds. So before embarking on this project, the most metal-poor star known in the LMC appears to have an Fe/H ratio of about -2.7. However, this does not reach the same extremely low metallicities seen in either the Milky Way halo or the very faint dwarfs. A recent paper by Reggiani et al. Also tell the same story, where they found 9 stars with Fe/H ratios ranging from -1.5 to -2.4 in the LMC. Therefore, one of the main motivations of this project is to conduct a proper search for EMP stars in the Magellanic Clouds using the SkyMapper telescope. The discovery of a confirmed EMP sample in the Magellanic Clouds, with Fe/H ratio of less than -3, is plausible and would have a very high impact, allowing us to shed light on the earliest epochs of star formation in the Magellanic Clouds and their possible accretion history of even smaller dwarfs. Ultimately, this would provide the missing link for galaxies between the two mass extremes of the ultra-faint dwarfs and the giant Milky Way. To begin searching for these elusive EMP stars in the Magellanic Clouds, we need to first create an EMP candidate list. The figures over here show the color magnitude diagram and the metallicity-sensitive diagram for high-priority EMP stellar candidates using data from SkyMapper DR3. This was cross-matched with Gaia to apply further cuts based on proper motion and parallax. This metallicity-sensitive diagram is a tried and tested method that uses a color-color plot to attempt to isolate and identify metal-poor stars photometrically. So the highest priority LMC candidates are labeled as yellow stars, which fulfill the criteria based on magnitude, color, and proximity to the -4 Dartmouth metallicity isochrone in blue. The red stars represent lower priority LMC stars, while the green stars are most likely SMC stars based on their positional coordinates. However, for our observing run, we only focused on the LMC stars. Based on this list, we followed it up by verifying their metallicities from low-resolution spectroscopy using the WISE spectrograph on the ANU 2.3 meter telescope. So here are the results of our search. We have produced a set of 7 LMC members with an Fe/H ratio of less than -2.75, and 2 of them have a metallicity value of less than -3, and these are considered EMP stars. So these constitute the most metal-poor stars ever discovered in the LMC. Yeah, so here are the spectra of the most extremely metal-poor star that we have found in the LMC. The 2 strongest lines that were used to determine metallicity are the calcium H plus K lines for the top spectra and the calcium triplet lines for the bottom spectra. The spectra of the calibration star is in black. Using spectrophotometric analysis, we can deduce that these two stars have the same stellar parameters in terms of effective temperature, surface gravity, and metallicity, which is confirmed by the close similarity of the two spectra. Our measurements for the calibration star are also consistent with values from high-resolution analysis in the literature. Hence, we can confirm that this star is indeed an EMP star. But to confirm that this star is an LMC member, more work has to be done. So the radial velocity of the stars, derived from the calcium triplet lines, were computed as a function of position angle in the LMC with the help of my supervisor. So the black dots represent carbon stars in the outer LMC disk, and the magenta stars represent our EMP stars. The sinusoid shows the rotation model of the LMC disk. As you can see, the radial velocities closely match the systemic velocity of the LMC for most of our candidates in the sample. Therefore, our targets are robust members of the LMC based on their 6D phase space information. However, as you can tell, the most discrepant star indicated by the red arrow is our most metal-poor candidate, which also has the largest distance from the LMC center at about 19 degrees. But it is not clear whether we should be expecting disk-like rotation that far out from the center of the LMC. On to follow-up plans for these EMP stars. I have also successfully obtained 28 hours of observing time to use the VLT UV spectrograph. So hence, by the end of this year, we will get high-resolution observations of the Magellanic EMP stars. This will tell us more about the chemical composition of the EMP stars, as we will be obtaining abundances for alpha, light, ion peak, and neutron capture elements for much lower metallicity range as compared to previous studies, as shown in this gray box over here. Specifically, we will also verify if the most metal-poor stars in the Magellanic clouds are R-process enhanced, which is one of the key findings by the recent paper by Reggiani et al. So to summarize, EMP stars can tell us a lot about the star formation histories of galaxies, and our search for EMP stars in the LMC using low-resolution spectroscopy have returned 7 stars with a metallicity value of less than -2.75, and 2 of them have a value of less than -3. So we plan to obtain high-resolution observations of the Magellanic EMP stars at the end of this year as part of our follow-up plan. Thank you.
Thank you, Wei Shen. Okay, so Joss has his hand up.
Yeah, that was very good. Very nice talk indeed. Very good thing to go after. I've always rather imagined, and I think the evidence is pretty strong now, that the LMC and the SMC came in as a group accretion event, along with globulars and other small events, dwarf-like events. So your observations are very interesting in that context, because I would have thought there would have been a bunch of ultra-faint dwarfs that came in with the Magellanic group, let's call it that. I think Dongier and Late called it that. I don't know how many UFDs, ultra-faint dwarfs, have been identified as being members of this system. I mean, I think it must have been done now by Gaia. Do you happen to know?
I'm sorry, I'm not too sure about this. Yeah.
Maybe Gary or someone knows.
It's about 4 or 5, Joss.
About 4 or 5, as many as that.
Yeah.
Yeah, and they're pretty clearly kinematically attached to this group, not to the halo.
Well, you can never be 100% certain, but those 4 or 5 are the best cases, yes.
Yeah, so it seems to me that you will find more if you keep going.
Yeah.
Yeah, I mean, they have absolute luminosities that are quite faint, but I wouldn't be surprised if the Nancy Roman telescope, sorry, LSST, whatever it's called, Vera Rubin telescope, might find some more.
Actually, I just wanted to make a comment about this because regarding like ultra faint dwarfs, so just going back to how we actually got our photometric candidate list. So it's based on the SkyMapper photometry. So we selected like one of the brighter candidates from like a range of 16 to 17 magnitude. So I'm not sure if whether or not we will be able to find any of these candidates from like the ultra faint walls, because they might be fainter or they might be further away from the LMC. But yeah.